Hello there, folks. So today I will be hosting this presentation titled Enabling More with Machine Learning. My name is Mohammed Hachaichi. I have a PhD in circular urban metabolism and climate change, and I'm currently interested in introducing middle-income countries into global climate agreements. I tend to orchestrate several research projects both within and outside academia. So the presentation outline for today, first of all, I will be starting by a brief introduction to machine learning. What is machine learning? What are the required skills? What can be considered as talented machine learning? What is the applied machine learning workflow? And what not to do with machine learning. In the second stage, I will provide an overview of machine learning examples from computer vision, natural language processing, data generation, and forecasts. In the second stage, I will provide some examples on what can be fixed by machine learning, such as weather and climate modeling, in pollination, sea level rise, protein structure, computing water availability, how we use, and finally we go to how we use machine learning in order to reduce the bias between the northern and southern hemispheres, and how to generate climate-related data for undocumented cities worldwide. And then in the following point, I will be speaking about the missing puzzle of machine learning, and whereby we will be discussing time-space complexity and data structure and algorithms. And then we'll go forward to what is your responsibilities in terms of machine learning and models, in terms of data bias, garbage in, garbage out, explainability versus interpretability. After we finish by how we can optimize our machine learning workflows, and that is by the several programming languages and specific modules, aka libraries or packages, and what are my current and future interest in using machine learning. So first of all, what is machine learning? So Arthur Samuel in 1959 defined that machine learning is a field of study that gives computer the ability to learn without being explicitly programmed. And then in 1998, Tom provide a much further and a much concise definition by saying that a computer is said to be learned from experience E with respect to some task T and performance measure P if it performs on T as measured by P improved with the experience C and T. And what it means is that we need to code a machine learning model that can fix a problem, but again, it needs to use the way that it fixes the problem to learn from this experience per se. And so overall, machine learning is about building algorithms that aim to mimic how the human brain learns and not works. So what are the types of machine learning? Well, first of all, we have the giant sphere of artificial intelligence, and then we have a subsphere, which is machine learning. Machine learning is also contain two subspheres. The first one is reinforcement learning, whereby intelligence agents interact with the environment that provides rewards and penalties in response to agents, which is a goal-oriented systems, such as things we can find in autonomous cars, for instance, in Tesla. And then we have deep learning. So what is deep learning? Which aims to mimic the activity in the layers of the neurons in the brain to learn how to recognize complex patterns in data. And for instance, again, the Tesla agents, they actually use deep learning framework and reinforcement learning framework to operate. What are the tasks of machine learning? Well, first of all, we can aggregate the tasks of machine learning into four main tasks. The first one, which is computer vision, whereby machine can analyze, understand, and manipulate images and videos. We have natural language processing, or NLP, which can enable machines to analyze, understand, and manipulate human languages such as Arabic, French, English, Chinese. And then we have forecasting, in which we build a model and saying, given a historical trend, events, and shocks, prevent what will happen in the future. And then we have data generation, saying that given a set of features and targets, estimate, generate data for unknown data points, whether they are quantitative or qualitative. What are the categories of machine learning? Well, first, we have three main categories of machine learning. We have unsupervised machine learning, by which, given a huge data sets, find latent structures, patterns, without any explicit labels. And then we have supervised machine learning, meaning that we have a data sets with targets, and then we assign the unknown data sets, the unknown targets of unknown data sets with specific targets. And then we have semi-supervised learning, which is also referred to as weak supervision, whereby noisy, limited, and imprecise sources are used to provide supervision signal for labeling large amounts of data. So now, what is the difference between machine learning and deep learning frameworks? Well, first of all, in machine learning framework, we have a given data set, and then we have a human being that is doing feature extraction manually, and then we use a neural network, for instance, to build the model. Instead, in the deep learning framework, we don't have the human agent in the process. So in deep learning, we have a given data sets. Let's build a model that can that can do actually feature extractions and can perform the model that we coded per se. So actually, the deep learning framework also learns from features and from the data per se. What not to expect in machine learning? So, for instance, this Ex Machina movie in 2014, directed by Alex Garland. This actually given insights or an overview of what might be the future AGI, or general artificial intelligence, but we are not yet there. So what are the required skills to be a machine learning engineer? Well, there are actually two paths to go to machine learning engineering. The first path is being as data scientist, whereby you need to have domain knowledge, you have to need engineering skills and diplomas, and then you will need to have a solid background in statistics and mathematics. In data science, mainly the big data approach is limited to gigabytes, and whereby we much consider the data constraints, and we often use a personal computer, where there is a second profile that can go to machine learning engineering, which is computational science. And a computational science can actually mobilize several specific skills. For instance, computer science, and then we have science discipline, for instance, complex systems or climate change, and then we have applied mathematics and numerical methods. In the computational science, the big data approach is often referring to petabytes, and then the constraints are mostly from the hardware part, and often computational scientists use cluster computers to do the computations. So what can be considered as a talent in machine learning and maybe in research in general? And this is just my overview. So the first thing is that we need reverse engineering skills, because let's say that we have a problem, and then Google Brain, for instance, in 2017, they published the paper of "The Intention is All You Need," compromising the transformers, the coder and decoder, and we want to use such new technology in our company. And so Having reverse engineering skills actually can push us forward to create the state of the art and examining the state of the art and understanding the state of the art. However, having only reverse engineering skills is not only sufficient, because we need to have critical thinking skills. And why is that? Because once we have the reverse engineering skills that can make us understand the state of the art, but critical thinking skills make us push forward the state of the art and ultimately leading the only path for me that can lead to innovation. Um, so what is the applied machine learning workflow? So first of all, we need to have a problem definition, whereby we need to define the problem, formal or give it formal and informal description, and list of assumption and the level of abstraction. We need to provide the data, the constraint. We need to highlight the constraints imposed by the data and define each attribute. We need also to show the motivation, meaning that the benefits and the use of using machine learning to fix such problem. And then we need to give a manual solution, meaning that an algorithm design on how our algorithm can fix our problem. But at this stage, it is highly important to show if the problem we are trying to solve is machine learning problem. In the second stage, we need to do some data analysis, meaning that we need to summarize the data structure and distribution, and visualize the data. In the third stage, we need to prepare the data, selecting the data, pre-processing the data, formatting, cleaning, sampling, and we need to transform the data, whether by scaling, decomposition, or aggregation. But at this stage, we need also to show if the data you have can actually solve your predefined problem. At the fourth stage, we need to create some models or algorithms and test the harness and options, explore and select some algorithms, and interpret and report results. In the fifth stage, we need to approve results, and this actually can be made by fine-tuning the hyperparameters of algorithm, or using ensemble methods such as bagging, boosting, and stacking or blending. But at this stage, also make sure that the fine-tuning process is significantly improving your results. Otherwise, don't do it. In the final stage, we need to present our result, and the result they need to be presented as follows. We need to contextualize our results. We need to state again the problem, and state the solution, whether we find solution or not. We need also to say what we have found. We need also to highlight the limitations of our method or our algorithm or our data, and we need to provide a fully comprehensive conclusions. At the final stage, we need to operationalize the algorithm per se, or the model that we have built. But at this stage, it is important to show that if the model can fix the predefined problem, as we highlighted, but also if our approach and our data can fix other similar problems. And this is actually what we call by a transfer learning, machine learning. So what not to do with machine learning? Well, first of all, let's assume that a given problem is a machine learning problem. So this actually is made upon a paper that I have actually reviewed, and it was the problem they tried to solve was not a machine learning problem, and I will explain this why and how. So first of all, let's say that we have a problem. So the first thing we need to do is to define the problem, to collect the data, to clean the data. This is the first thing. So the first approach is to use a classical approach, meaning that we are trying to use classical regression and classical statistics, and then we analyze the data, and we provide results. So that actually the authors that have found, let's say that the results were X1 and Y1. The authors said that we can actually use machine learning to enhance our work. So what they have done, they have provided a machine learning approach in which they have selected a machine learning algorithm. They have fine-tuning the hyperparameters of the four module that have chosen, and then they have ensemble methods backend. They have integrated the Uber algorithm, which is minimal redundancy, maximum MR. Um, and then they made the analysis and they have set the results. And one of the main problem is that they have found that the conclusion was actually, and the results were actually, they have found X1, Y1. And so they have actually lost a lot of time to show the same thing. And this actually shows that not all the problems are machine learning problems by nature. So let's now provide an overview of machine learning and how it's being used in science generally. So the first example is a computer vision from the Event Horizon Telescope, in which a group of scientists, they have collected several data from telescopes across the world, and they made several data collaboration, of course, and then they have used an algorithm to generate the first pictures of the black hole. The second example is natural language processing of the generative pre-trained transformer Gen 3, which is built over 75 billion machine learning parameters, making it the first large pre-trained model. It actually surpasses Microsoft Turing NLG model, which have roughly 1 billion parameters. GPT-3 is currently considered as the largest neural network ever produced by human beings. It cost $12 million for a single training run. It can perform on all NLP tasks. Microsoft actually have invested 1 billion US dollars to be the only licensee for the GPT-3. However, there are several limitations of the pre-trained natural GPT-3, because first of all is limited training, given the fact that it's a pre-trained model. It is unable to explain and interpret output because it's black box model. It can actually feed on small input size, which reduce its usefulness. And then there is a wide range of scientists that they have shown that the GPT-3 is actually biased, and it promotes conspiracy theories and white supremacy. Let's speak now about data generation. Again, the model GPT-3, because it's the most fascinated pre-trained model. So the first example is generating natural language processing. Given a word, give me a definition, or let's say something that can show to describe the word. And the second example, the GPT-3 actually can be used to describing the Google layout page, and then it generates the code, the HTML code, to generate the first page of Google, which is actually insane. So in terms of forecasts at scales, Facebook have provided the library of profits, which deals with missing values, shifting the trends, and outliers. It is actually accurate and fast, fully automatic, tunable forecasts available for R and Python. Facebook has announced neural profit, a hybrid forecasting approach pre-trained with deep learning and based on PyTorch. Machine learning is also used in weather and climate modeling. For instance, the Deutsches Klimarenkenzentrum and NVIDIA, the collaboration between the two companies have led to create what we call warm data at the global scales using partial convolutional neural network model. how actually machine learning is being used. Also, we have the pollination from, we have an example for Arugga AI farming, which produce tomatoes in Israel. So we know that tomatoes requires not only water, soil, and sunlight, but also pollination. We need to pollinate the flowers so we can have tomatoes. Albeit that the plants are self-pollinating, they actually required some help to drop the pollen into the female organ so we can actually start the pollination process. And given the fact that we don't have a lot of bumblebees nowadays, the Arugga AI farming, they have built a robot that determines the plant ready for pollination and blasts air pulses to initiate pollination. The robot actually uses computer vision algorithms, so it can define what are the plants that are ready for pollination. Alongside that, the pollination process, the robot actually collect and analyze the data along the way. Um, the other the other way on how machine learning is currently is being used is to predict protein structure, and this time is by DeepMind team, or they have provided what we call the AlphaFold. So we know that the protein structure means defines the protein function, and 100,000 of, and we know that 100,000 of the protein sequence are known, but still billion are still anonymous. So the DeepMind group have used large-scale structural bioinformatics through accurate computational approaches to define 3D structure of a given protein is based only on the amino acid sequence. And this is actually a major breakthrough in science, and I actually believe they will at some point gain a very prestigious prize in science, let's say maybe the Nobel Prize. Machine learning is also used to estimate the sea level rise. There are scientists actually from the US that say, we know that by 2015, 250 million of people are at risk of sea level rise, given the fact that sea level rise will be rose by 20 to 13 centimeters with a high confidence. And so the researchers, they have used a multi-layer perceptron to evaluate the sea level rise across the world. Um, how how can machine learning be used again? So we have the computing water availability. So for this project, which I'm currently doing, we want to estimate the precipitation at the catchment area for the city of Cape Town. And so what we have used is that we used a partial convolutional neural network model using a transfer learning approach. In total, we use 17 climate parameters and 3 scenarios to evaluate to compute and estimate and predict the water availability in dams and also in the catchment areas for the city of Cape Town. How we are currently using machine learning to reduce the bias between the north and southern hemisphere. First of all, let me just explain that there are two names, but they have different interpretation. First of all, when I speak about global north and global south, I mean it have a different interpretation, and it focuses mainly on affluence, and this is where we are using it in the carbon footprint project. And then when we use the term, when I will be using the term of northern hemisphere and southern hemisphere, I refer to the geography, and it is used in the Water Food Energy Nexus project. So the northern hemisphere and southern hemisphere are countries that are divided by the equator. So why we need to reduce the bias between the northern hemisphere and southern hemisphere is basically to provide equal opportunities to sustainable growth, and because we know that the old keys don't unlock new doors, and we actually see in machine learning a new approach, a new method that can actually reduce the bias between the north and the south. So in the first project, which is the water food energy nexus, we know that the water, food, and energy are important for human well-being, and they are recognized as being a human right. However, the problem is that the northern hemisphere is developed and produces a lot of knowledge in terms of literature on the field, and we need to support cities of the southern hemisphere with less urban intelligence. So our research question was, how can we initiate a transfer learning program from the northern to southern hemisphere? So what we need is, as targeted data, is publication and what we call actually big literature. So what is the required machine learning field? It's natural language processing. So what have we done? So our database actually compromises 32 more than 32,000 case studies covering more than 2,000 cities worldwide. Cities covered by our database are actually hosting nearly 15% of the global population. So what is our motivation for this work? We need to mobilize the bottom-up case study knowledge to provide synthesized water, food, energy nexus knowledge at planetary scale. However, what do we know about what the scientific literature says about case studies? Well, first of all, we have some quantitative scientists undermine actually case studies because they lack of generalizability. Because given case study, it can actually depict the project in hand and cannot actually depict the problem elsewhere. However, there are some other quantitative scientists that emphasizes on a mature case study can lead to generalizability, and also the new insight and the knowledge gained in terms of additional values as the case studies inspect the relationship between the science researchers and policy, which is policymakers. So what was our method? So what have we done is that we perused we made a literature scooping. We used Science Direct and Scopus as database. We use a given query, and by the end of 2022, February 2023, the metric retrieved 164,000 documents. However, it's highly important to know that the 164,000 documents are only in English because other languages has been excluded, and this actually can be considered as a limitation for the current study. So data pre-processing. So what have we done? So to identify the case studies, we searched in the corpora for city names. We found that more than 32,000 document case studies. And the assumption actually afterwards was validated by reading a sample from the data set. However, it's important to highlight that the Paris Agreement and Kyoto Protocol were removed from the algorithm to avoid any false matching. And then what we have done is that we created term frequency inverse document frequency matrix, and then we applied the non-negative matrix factorization to generate topics for each case study. So what we have found is that before 2011, the water, food, energy nexus was mainly considered as a bipolar approach, focusing on food and energy. And then after 2011, after the Bonn conference, it became motivated upon a tripolar approach of water, food, and energy. We have also found that the three main methods used in scientific literature are the life cycle assessment, input-output analysis, and decision support. What has been found is that actually there is a huge bias in terms of the water, food, energy nexus knowledge production, whereby the north detains 94%, and the south contains only 6% of the global water, food, energy nexus production worldwide. What we have found also is that not only there is a bias in terms of between the northern and southern hemisphere, but also we have found is that after the conference of Bonn in 2011, Asia has started to produce water, food, energy nexus knowledge production, but Africa and South America, they actually did not improve significantly. What also we have found in this research is that medium cities and large cities are severely underrepresented regardless of their share of the total global population. And examining the trend of the topical trend, we have found that the topics of climate change modeling and sustainable cities policies, development, crops, productivity, and the impact of drought, wastewater treatment, and temperature effects on on water availability are they are currently growing in the literature. What we have also found is that there are some shortages in terms of the topical panorama of cities, of southern cities. For instance, one city focuses only on one single topic, and this is actually a problem because we need that cities focus on different topics so we can actually initiate the transfer learning from the southern to from the northern to southern cities. And we, after we want to make just one single synthesizing this water food energy nexus problem. And so what we have found is that the northern cities they focus more on water and energy, and southern cities they focus more on water and food. And this is actually a problem because we cannot actually say, let's take a given case study from the northern hemisphere, say see what they have done, and then let's transfer back the knowledge to southern cities because they do not have the same focus, and this is actually a problem. And what we are currently working on is we need a transfer learning protocol, meaning that we need to have a lot of case studies. We need to rank and shake and shuffle the case studies and then make case study selection or protocol that can only works with the southern city hemisphere. So from now on, the southern hemisphere dictates the algorithm and how what are the case studies that should be selected. To build expertise and learn from Watford Energy Nexus knowledge production from Northern Hemisphere, actually we have two selection procedures that are critical. The first one is the selection of the case study per se, and here we are talking about the feasibility. And then we have the case study location, and here we are talking about the geography, because there are two extremely and ultimately important criteria. And the second project we used, we generated carbon footprints for undocumented cities. The main statement was that to tackle climate change can be possible only by computing the GHG emissions. However, for most cities, towns, and rural areas around the world, no carbon footprint has been estimated before. So, what is actually our problem? We know that the climate change is a planetary problem and that all humanity must face collectively and distinctively, but GHG emissions distribution across global regions is still anonymous. Our research question was how to estimate the carbon footprint of places where there is no sufficient data. So the targeted data is previous carbon footprint projects, and the required machine learning field is estimation and prediction or data generation. So what have we done is that we constructed a database comprising the carbon footprint of more than 24,000 cities across the world. The motivation of the research was we need to estimate the carbon footprint to help understand and design a new future climate pathways and to add middle-income countries into the global climate agreement. What the literature review said. So currently the literature review said that African and Asian cities are growing significantly in terms of size, population, GDP, and their carbon footprints remains poorly documented in the scientific literature. Cities' carbon footprint inventories of the global south are hampered by the lack of local climate data, reduced climate footprint, and shortages in climate finance. The current focus of literature on large megacities is not actually justified, as there is just 12% of the global population living in megacities compared to 43 that lives in small cities. And we know that North America, Europe, and Oceania are very well documented despite their small share of the global population. So what we have done is that we use scientific output research project with the same attributes that have used input-output analysis, EURA as databases for input-output tables. And they used consumer expenditure surveys, and they have used the metric of term CO2 per capita per year. All the features from the ecological footprint network and World Bank have been downloaded and pre-processed. So what have we done is that we made a differentiate between urban and rural carbon footprints. And after what we have done, we tested a set of models and we implemented and tested, and the model with the highest performance metrics was selected. And then what we have done, we explained the model fairness in terms of additivity and consistency, because we want to know how much we can be confident and how much we can trust our model, because you know that we are experts, and we want to know if our model uses the same features in the way that as we have the domain knowledge think it should do, and actually the model actually uses what we wanted it to use. And afterwards we have some data and output, and we discussed the data between the northern and southern hemispheres, global south and south, and global north and global south. One intriguing finding is that we found that 0.06% of cities actually they could achieve a higher human development index with less than 5 tons CO2 per capita per year. The case of Ramat Gan, Jerusalem in Israel, Osaka in Japan, Buenos Aires, Naples, Limassol, Paphos. And this is actually very intriguing because we are currently studying how these cities actually are behaving, because as what it appears is that they have a sustainable and pro-climate patterns, lifestyle patterns, and we want to learn more how they are evolving and behaving, and what are the dynamics, the urban dynamics in these cities. So after all, what we have done is that again we want to help cities of the global south, and taking reference from cities of the global north. And so what we have found is that there are actually 3 clusters. The first one is outer mutual learning, meaning that same cities in the same country can learn and initiate transfer learning programs. We have found also another cluster of cities of cross mutual learning, meaning that same cities of the same continent can actually work together to cut urban GHG emissions. And then we have the third cluster, which is an inner mutual learning, meaning that there are cities in a cross continent that can actually work together to cut urban GHG emissions. So what is the missing puzzle of the machine learning? And one of them is the time-space complexity. So what is the time-space complexity? So the time-space complexity is how much the algorithm takes time and how much it consumes RAM to execute the coded task. And so we will be introducing the big O notation, which is the complexity chart, and we need to select the most efficient algorithm when the problem can be solved with different methods. So for instance, in our Water, Food, Energy, and Access project, the time complexity of this project, the time it takes actually 2 hours to run all the total Python script. And we have a function that takes a lot of time, which is the geoparsing function. So in which we iterate over the literature review and find city names. and the space, it takes roughly 9 gigabytes to store the term frequency inverse document frequency matrix. So again, times space complexity. So we have this another project that I'm currently working on virtual water, and we have the first code. And in the second code, what I have done is that I have specified the place to store the output of each code offline in the RAM, and so I could actually achieve 11% faster than the previous code, which is actually pretty amazing. The missing puzzle of machine learning is data structure and algorithms. So now let's speak about data structure. You need to choose your data structure, how to better store and retrieve your data. For instance, in Python framework the data structure, we have primitive such as integers, boolean, string, and floats. And then we have non-primitive data structures. We have some built-in data structures such as lists, sets, dictionaries, tuple, arrays, and data frames. And then we have the user-defined data frames such as stacks, queues, trees, linked lists, and graphs. And you need to choose a very specific data structure so your algorithm runs smoothly and fastly. Again, not only the data structure that is important, algorithms are also important. So let's say that we have given this array, sort the array. For instance, we have three sorting algorithms. The first one is quick sort algorithm with the quick sort algorithm. The second one is straight insertion sort, and the third one is heap sort, which is not actually stable. And so you need to also choose the algorithm, the most efficient algorithm, because some algorithm handles small amounts of data but performs very slowly whenever the length of the array or the data becomes very large. So implement wisely whether data structure or algorithms. And the reason why data structure and algorithms are important because you need to scale up your model, and scalability matters. Every model should be scalable. What are your responsibilities in terms of machine learning algorithms? So the first one is, of course, data bias. Let's assume that you have a data set and then you have two types of data, and you took only a small subset of the data set as a training data, and then you do not actually take the other type of the data. And so the algorithm and the model you will produce will be also biased. So one way to fix or to highlight whether your model is biased or not is to use a cross-validation model, meaning that you take several subsets of data sets and then you feed it to the model, and then each time you evaluate the performance of the model. One of your responsibility is also garbage in, garbage out. Let's say that the movie was filmed in, and let's give it a name of countries. So what I have done is that from Transformers Urban Import Pipeline, and I used the pipeline of the sentiment analysis. For country involved names unique to list, what I tried to do here is create a loop, take each country name, put it in the line the movie was filmed in. For instance, here I give a simple example. So the movie was filmed in Spain. It's positive sentiment analysis. And then we have the movie was filmed in Turkey, and it's negative sentiment analysis. And so this is actually why, because there was a lot of garbages that is currently existent on the internet, and the large pre-trained model are actually trained on internet data, and therefore they are actually maintaining inequalities, bias, and they are not actually very accurate, and they are unfortunately black box approaches. And the reason why is that you need to train your own model, and you need to stay away from pre-trained large models. And the reason why, because we need large models are black box approaches, and we need to transparent model. So let's say that here that this patient has a 97% likelihood of pneumonia, and I don't want that. I want to know why this person have pneumonia. And then if I want to know that because this region is abnormal. But again, in this example, we don't know why, for instance, Turkey is negative, why Germany is negative, why Saudi Arabia is negative, why South Africa is negative, right? And why Spain is positive, why Canada, Mexico, and the United States, France are positive. We can't actually explain that because it is a black box model. So this is why it is highly recommended to stay away from the large pre-trained models. One of the way you can optimize your machine learning approach is that you can actually work with simultaneously two programming languages. For instance, I used Python to do some climate, to process some climate data, and then at a given stage we needed a lower programming language such as Fortran to make a very specific task, and we actually use the two in a given project. So this is why actually it's highly important not only to master and to learn the higher programming languages such as R, Python, and Julia, but also to learn to code in lower programming languages such as C and Fortran. One way also you can optimize your machine learning workflow is, for instance, using Dusk, which can provide lazy data frames, using X-rays, which is largely used in climate science. You use TensorFlow, PyTorch, Keras, Keras for deep learning frameworks, Scikit-learn for machine learning framework. You can actually use GitHub as version control. You can use OpenCV for computer vision. You can use SHAP for model fairness. You can use Theano for optimizing mathematical equations, mathematical computations, especially with high dimensional arrays. And you can use also Teapot, which is a machine learning library. What are my current and future works? So, for instance, in academia, what I'm trying to do is to settle the decision about for case study selection, aka designing the transfer learning protocol. What I will do next is decomposing cities' carbon footprint by major consumption categories, for instance, transport, food, agriculture, industry, services, and suggest affordable actions to cut urban carbon emissions. I'm currently actually estimating poverty for global south using a subgrid scale with a high resolution, using machine learning and very customizable neural network in computer vision. I will aim to fast forward the mutual learning between the north and the south using deep learning. I'm also computing the planetary boundaries at city scale level worldwide. I'm trying to evaluate the climate impact in North Africa, such as migration, biodiversity, and resources. We know that North Africa, such as Morocco, Algeria, Tunisia, and Libya, is considered actually as a hotspot for climate change. And people actually, in a few years, they will initiate migration towards Europe, and it's better to study and be preventive in such impacts. And the final work that I'm currently doing is simulating new climate pathway using agent-based modeling with social and environmental constraints. And in terms of outside academia, I'm creating the What's Food Energy Nexus platform using the BERT, bidirectional encoder representation from transformers. and I'm trying to create software to generate the genesis of given research field, to summarize the literature review, for example, to write the introduction parts of articles or PhD studies or master theses, to help in writing the literature part, and then estimating and predicting sea level rise in urban coastal areas, which is work currently in process. So if you have any inquiries, questions, inquiries, please email me. Thank you for your watching. Goodbye. See you in the next video.